representation. Do you remember that the loss function here, I can always represent them in terms of these forms here. Let's say do 2m here to be x theta minus y, take enormous of that. So that's in the matrix representation. What does this loss function look like? And I mentioned that you can also rewrite them into this way here. 2m here, x theta minus y, take transpose to be x theta minus y. So that's how do we calculate the norms of this vector space. And now you can see, as a result, this guy here is simply is a quadratic functions of the theta. So because it's a quadratic function, you can calculate the gradient of L with respect to theta. And in this matrix representation here, essentially you're going to view this as if it's a quadratic function here. And you have 1 over 2m is a coefficient in front of that. You have x theta minus theta here. You're going to do x theta minus y. So that will be quadratic because of the quadratic terms of that. So now I need to take gradient of x times theta with respect to theta. So that would be matrix x here. So if we want to make this matrix dimension matches here, you're going to put the x here, take a transpose in front of that. And that is the gradient of loss in terms of this in this kind of matrix representation without kind of loop representation. In the matrix representation, that is the gradient of loss with respect to individual parameter. And you can confirm you that this is exactly the same as this guy's here. And the only difference here is this is written in this individual component. Here is written in this kind of matrix representation. Because I do divide by 2, I don't have 2 here. I can divide this 2. Simply n. Okay? So that is in terms of the matrix representation, what is the gradient of loss with respect to parameters. And that more or less complete the way, how do I update my parameter theta. So let's revise what